like, 3 or 4 punches from your mouth.
Yep. So my name is Michael Riley. I'm with Carnegie Mellon's. I'm with Carnegie Mellon Software Engineering Institute, and I run a group there where we take a look at the resiliency of critical systems. And our goal within this group is to identify methods and technologies to ensure that if there is some sort of anomalous behavior, that behavior can be detected and mitigated. Tony, he can't join us today, but he helped us out a lot on the machine learning portion that I'll talk through a little bit later on. Obligatory legal slide. And so from a cybersecurity perspective, there have been some great discussions so far at the conference. And last night's discussion teed up a bunch of threats. And in that teeing up of threats, I thought it was great for some of the foundational stuff here. Within cybersecurity, there's essentially 3 pillars: exploitation, attack, and defense. And exploitation is often called or often a part of exfiltration. So we see that a lot with our credit cards. We see that a lot almost every day in the news. There's some other major exploitation event. But it's more than just exfiltration. It's also placing a rat or a piece of malware. RAT, by the way, is an acronym for Remote Access Trojan. And so those types of malware that gets placed onto processors is also a part of the exploitation doctrine. Attack is one of those other pillars, the second pillar. An attack is about ensuring that a particular system cannot form its mission. It cannot complete its mission, cannot behave as anticipated. In some instances with spacecraft, it's fathomable that an attack actually leaves the control of one organization and goes to another organization. Obviously very bad. And then the portion of cyber that I'm going to focus on in this discussion is defense. Ensuring that our particular piece of hardware can be and will remain with us. What are the identified methods, and what are some of the fundamental controls that we can put in place to mitigate that threat activity? So let's consider for just a second what would happen if we were to face some sort of cyber exploitation on a spacecraft. Where would that malware go? How could it be identified? And what are we going to do about it? So some of the fundamental questions that exist in the space. And the obvious answer is memory. Very few spacecraft that I've heard of have spinning media. It just doesn't exist. It's solid state. So if that malware or if that remote access Trojan were to hit spacecraft, it would end up most likely in memory. So we're going to talk through some memory. We're going to talk through some foundational stuff here. I'm also going to touch on the pitfalls of traditional cyber anomaly detection. Why that won't work in this space. I'm going to then go into some of the proposed monitoring techniques that we can use on that memory. I'm going to talk through this notion of a performance and security model. And I'm going to talk through how that can be used as almost an oracle, or what does right look like, and fly that on board the spacecraft to do some comparisons. Finally, those analytics that I talk about in that last sentence there, we're going to touch on those and how those can be used within a model to determine whether or not the memory is as I anticipated. So, in general, memory segmentation will look different than what I have here. This is a notional representation, but it includes some of the foundational concepts that we find in the text, the data, the heap, and the stacks. This particular type of a memory load might be for a structured language, structured compilers. Obviously, if I have an object-oriented language, I'll have an initialization in a finite area. But it is just, in general, a list of the various segmentation areas that I would find. So let's talk about that text area. the lowest area of the segmentation, the memory segmentation. This is often the area where I bring over memory content from NVRAM, and it starts at a very low level. This is an area that's often set to read only, so that stuff isn't copied in there on a routine basis, so it doesn't change. As I bring over that particular machine instruction, as I spawn tasks later, I'll often spawn them right out of the text segment. So the data segment. This is going to contain a lot of my global variables, a lot of my statics, a lot of my constants. If I have predefined memory shares, I'll find that in this particular area of memory. The heap. The heap is obviously the largest portion of memory that I fly on board or can be found inside of memory segments. The heap is where a lot of the dynamic allocation occurs. It's this large portion of memory that I actually build the stacks from. They originally start out of the heap. And of course, each one of my tasks, my flight software tasks themselves, are going to have stacks. And that stack is a predefined set of memory that it's used to process a set of instruction code specific and unique to those tasks. So in general, this right here is just a concept of what I would see in a traditional memory segmentation list. So now that I've talked through what general memory might look like, I'm going to talk through some of the traditional pitfalls that cybersecurity, as it's been done in the traditional past, why that might not make sense for flight software. And the first one comes for signature-based IDSs and antivirus. This particular challenge is such that if I have to see the information, if I have to see that malware one time, I have to capture it, I have to identify what its unique signature values are, I have to store those, and then I have to get it to some location so that I can compare it against memory. So this particular process is relatively burdensome. Finding a piece of malware for the first time in the wild, identifying what those values are, and then getting it to a spacecraft. It happens every day on ground. It happens every day with the major malware, virus total companies that exist out there that capture these pieces of malware and send out signatures. But when it comes to spacecraft, I'll use a lot of my bandwidth in just sending these pieces of information up. And I don't always have that sort of luxury. So that particular approach will not work here with spacecraft. Specifically, the other thing is, and in terms of real-time behavior, I'm processing a constant amount of information, and often I don't have the resourcing power to constantly compare against a known piece of malware. I have to be able to work on my mission, and I don't have a lot of the necessary resources to do a lot of comparisons as I look for that malware. And finally, threat actors, the bad guys. If they're going to attack a spacecraft, it's fathomable that they're not going to use a piece of malware that they've used on ground where a signature already exists. It's more likely that they're going to use a piece of malware or a rat that hasn't existed previously. And so we'll see something new for the first time. And if we're going to see something new for the first time, then this methodology isn't going to work, at least not for a lot of the spacecraft that might potentially become compromised in the future. So what I'm going to talk through now, and in fact, I think I'm missing my first line up top there, is an anomaly detection overview. So we talked earlier about the memory segmentations. I'm going to touch on the notion of a security task manager, an actual piece of flight software that would be used to spawn and to do the housekeeping of a lot of the flight software tasks. I'm going to talk about a performance and security model, a model that is essentially an oracle or a definition of what right looks like for those flight software tasks. And finally, I'll touch on analytics. The analytics that make the comparison between what is real today, what should right look like, and make a determination if there is some sort of anomalous behavior. So a security task manager. A security task manager is not unlike traditional task managers that might be found in an embedded system. This particular task manager might spawn tasks. It might keep track of memory queues. It might retain stack informations, location information. It might also understand what happens when terminating tasks go away, cleaning up that particular space that existed. And so this right here is a somewhat of a parental task that just monitors and keeps track of the flight software tasks as they come and go. But in particular, it would look for the task control block attributes and pieces of the task that might identify where they live at in memory. So, the text and the data segment meant monitoring. We take a look at that flight software task, and one of the things that it must do is understand what changes might have occurred in the data and the text memory segments. And our intention with the flight software task, the security manager, is to make some comparisons, but do it on a periodical basis. We've played around in the lab with doing it at 1 hertz. That's very, very time consuming and resource intensive. But somewhere around that 5 hertz model on a power PC makes a little bit of sense. So we can make those comparisons of what's in the text segment, what's in the data segment, with what's stored in the actual performance and security model. And we can also take a look at what it looks like for A or B side type processor, where we might have a B processor in case there's a hot swap that's required, to make sure that those two are aligned as well. Task watermarking. This is also a function of the security task manager. As tasks are spawned, they're given a little bit of stack to run in, 200, 300, 400K, or whatever the need is. And as that particular task is being spawned, and I give it stack, one of the first things I want to do is paint that stack with a repeating pattern. By repeating it with a pattern all the way through the actual memory allocation, I can then create a watermark level. As I initialize that task, I use some of the stack. I start down at the stack base, and I might go all the way up to the stack watermark. As I do that, the pattern that was initially created there is erased, and it's filled in with the actual contents of the stack, the actual contents of the task. But as my process goes on throughout the actual task, my stack pointer could change, although my watermark level will not. My watermark level within that task will hit a peak and stay there. It's fathomable that that might grow over time as new parts of the tasks are used, but for the most part, that watermark level will be somewhat static. Therefore, from the stack size all the way down to that watermark level, it's fathomable that that will not change much, although it might change some and get smaller. It should never grow. The watermark level should never decrease. And so based upon some of that information, I can identify from my anomalous behavior that if I grow beyond the allocated stack size, huge problem, right? I've not given my task enough stack to run in. And if I actually go backwards, if I shrink, that's a piece of anomalous behavior that I want to see as well. And if I have unanticipated watermark growth, why is this constantly growing? That might be an indication of some sort of a memory leak. So there's a variety of things that I can gather just from watching the task watermarking for each one of my flight software tasks. course, I have hardware and OS to look at as well, and I almost can't separate them here. So I wanted to touch on them from a actual task manager, security task manager look. I will have, or it's possible that I might have, hardware exceptions. Now, although I've seen these things on flight a few times, they're usually an anomalous set of behavior. It's something that I don't want to see on a routine basis. So I don't watch for it. And when one of those flight software tasks do occur, when one of those exceptions do occur, I want to consider that to be anomalous. That's an area that I want to dive deeper into to find out why those exceptions are occurring. And of course, watchdogs, very common in the flight industry. I've seen them at 2.5 times the duty cycle or the anticipated cycle, but they can be 3 or they might even be 1.5. Either way, as that watchdog checks in for a certain amount of flight software tasks, you could fathom that it changes. The delta of its check-in frequency changes. Although it has to have a hard boundary at 2, 2.5, 1.5, it might always check in at that one duty cycle or 1.2 duty cycles. If I'm seeing changes or deltas in that over time, that's also an indication of potentially anomalous behavior. And certainly if I see it checking in less than 1 duty cycle, I definitely have anomalous behavior where I want to check in and understand that even more. Now let's talk about the heap. The heap is that area where we're constantly pulling in dynamic memory. Well, as those flight software tasks are initialized and they have to get some dynamic memory, you'll see a lot of clustering when tasks are first initialized. That clustering that happens inside of Heap is unique to each particular task in terms of its task vars and some of the dynamic memory that it needs. But the most amount of it that I see out of the gate or the most predictable amount, is right there at the initialization time. So one of the great things about ML, machine learning, is I can create the data. I can create the data here, a predictability amount for each of these tasks, when they're spawned, when they take up a certain amount of heap, and start to predict it. I can predict that usually from when the task first starts, but as I talk about in the next slide, as the task is constantly consuming more and more dynamic memory. So at runtime, Heap is also going to be consumed or taken up by those individual flight software tasks. But it's going to be in a predictable way. It's usually in a predictable way based upon the progression of that task over time. And what I've seen, or what we've seen in the lab so far, is this is an ideal time for training. Training the classifiers, for those that are familiar with a lot of the traditional ML. We train those classifiers based upon each individual task. And then we aggregate each set of those individual training amounts so that we have some general knowledge of how that task grows over time, how it pulls in more and more of the heap so that it can be used for dynamic memory allocation. This particular set of training helps to build that classifier so that the classifier itself can then be added to the security and performance model. And as it's added to the security and performance model, I don't need all that ML data on flight. I just need the classifier. And I'll use that classifier to watch for the constant pulls from Heap for dynamic memory allocation. So let's talk a little bit now about that performance and security model. It can't be that large. It's a persistent data store. It has to live past power cycles. So it'll live in a non-volatile RAM, be initiated, and then potentially I'll have to be able to save some of that content as the flight software continues to evolve. If not, then I have to be able to go back to a known state to pull that particular performance model in. The size depends obviously on the hardware. Ideally, it will be predefined with values of what I've measured already on ground so that I can compare it in flight. I see the V&V cycle. I see a variety of ground-based exercises needed to build that security and performance model. And once again, that performance model is what is used to identify what right looks like. And I could see it updated at very low priorities. And by doing so, I don't interfere with flight software, the actual needs of the mission set. And the final thing I'll talk about for the performance and security model, I see 2 copies of it. One for flight and one on ground. The ground being a digital copy, a digital double, so that as telemetry comes down and talks, and that telemetry identifies where tasks are spawned from, what type of allocation of memory might be existing, based on the available telemetry I can get, I can model that or replicate that on ground to also look for anomalous behavior for when I might have malware or rats that could be introduced into the system. So now let's talk about analytics. This is the heart, the true heart and soul of a security and performance model. And the fact that those analytics are what measures what is occurring in memory at any moment in time, and then compares it against that model that's been developed on ground, is now flying, and potentially has been updated. So these analytics will identify things like task attributes. Where does the task live? How big is its stack? Has the stack pointer changed, or has the watermark level changed? It'll tell me things like, have I actually lost particular stack sizes? What about my message queues? How have they changed? Has the message queues actually been overpopulated? Has there been an overrun of a particular task stack? Also, from a dynamic memory allocation standpoint, as my memory changes, and it's gone from an initialized state, it's constantly gone through and I've pulled more dynamic memory out. How has that been compared to what I've measured before in my security and performance model from my classifier for ML? How has that changed over time? Of course, my analytics can help me out with watchdog check-in frequencies and of course some processor exceptions as well. And then what happens when I do find something? What happens when these analytics actually do identify anomalous behavior? Well, it's fathomable that if you're in a cyber contested environment, a lot of that information might not make it to ground. So there's certain things that can be pre-programmed to deal with anomalous behavior on orbit or on flight. Time. Sure. So identified here are some potential methods to deal with mitigation, and ideally we'll have a lot of ground-based information for trending and hardware behaviors in the future. And that's all I got.
Well, let's take one question, please. Any questions?
I think space systems bring an interesting aspect to bring to play here, and that's that we're not limited to von Neumann architectures for our systems. We could have, as you mentioned, watchdogs. A lot of times that's watchdog processors. I'm curious, you know, I'm sure there are people who are designing interesting multi-path buses and stuff to handle some of these issues, but something to consider.
Okay.
What was there?
Was there?
That's not really a question.
Okay.
Your thoughts.
Okay.
So Harvard architectures come into play here. There's a variety of different architectures from a control to data standpoint. There's a lot, to your point, there's a lot of different, it's not always the same type of processors that you see on ground. I concur with the gentleman.
Great. Thank you very much.
Thank you.
So to let everybody know, we have